Good evening, everyone. Welcome to week 9 problem solving session for the Analog Electronic Circuits course. I'm D. Sharda Devi, a PMRE fellow from IIT Gandhinagar. So, somebody could you please confirm if I'm audible clearly?
Yes, ma'am.
Okay. So, with this, let's get started. So, today also we'll be discussing basically like differential amplifier based problems. We'll look into some capacitance based problems. So let's begin. So this is our first problem for today. So if you have any doubts, please don't write in text form. Just unmute yourself and interrupt me anywhere possible. Okay? So yeah, in this given circuit, it is a single stage fully differential amplifier. Fully differential C again. Fully differential, why fully differential? That is because you have two inputs and two outputs. So it's doubly ended, like a double-ended output. So that's why it's also called fully differential amplifier. This is one of the names. So here the device parameters have been given for both the transistors. For both the transistors, Kw by L is common. VTH P, since they are matched transistors, right? So keep in mind that always the differential pairs which are designed, they are matched pairs. So practically that is not possible. That's why you get that CMRR, or you could say the common mode gain. But otherwise, if we talk theoretically, they should be ideal. Like they should be matched transistors. So both the transistors or all the transistors that you use in the symmetric pair should be similar. So that's fine. Now lambda we have 0.01 V inverse. The value of components RD1, RD2 are 1.6K, 1.6K, and we have RT of 1K.
मैम आवाज
Yes.
थोड़ा सा कम आ रहा है मैम
Sorry.
आवाज कम आ रहा है मैम थोड़ा सा वॉल्यूम कम है
आवाज कम आ रहा है मेरा.
यस मैम
अब ठीक है. Hello.
यस मैम यस मैम
Okay. So yeah, VDD is given. Common mode bias is also given. So that means 5 volts is being applied to both the sides. Now refer to the circuit given. Let me copy the circuit first. Find the maximum output voltage swing towards negative side. We have to find the maximum output voltage swing towards negative side from the sinusoidal input voltage signal. So basically we know that there is a swing, right, across your output. So you have to tell this value. This is what is asked, this particular value. So this is the swing on negative side, right? So just for the circuit, first of all, what are the things that we know? We know that the current that would be flowing in both the branches, let's say I1, I2, would be equal. And here you have a PMOS. So here it is VDD. Let's say at this point is Vx. So VDD minus Vx upon RT will give us the total current I. and I is then distributed as I1 plus I2, where I1 equal to I2. This is what we know. Now, if we observe from here, I1 is also the current that is flowing through a transistor, right? So I can write I1 as kW by 2L V is G minus mod VTH K whole square. So that is kW by 2L. Vs is how much? So this is source, gate, drain. So Vs is actually your Vx. So Vx minus Vg, Vx minus Vg. Let's write Vg for now. Minus 1 whole square. Now we know that I equal to 2 times of I1, right? And I we know from here. So this is I that we know, this is I1 that we know. So why don't we equate these two through this equation? So we have 2 times of kW by 2L Vx minus Vg minus 1 whole square equal to VDD we know 12, so I'm writing 12 directly. 12 minus Vx upon 1k, right? Okay. So here, this two are cancelled. Now here we will have, this is 2 milliamps, pi square, Vx minus Vg minus 1 whole square, equal 12 minus Vx by 1k. If we multiply it here, we'll get 2. Then Vx minus Vg minus 1 whole square, 12 minus k. Now from here, this VINC, that is V common mode, is given 5 volts, right? So if there is no signal present at present, then too your VG will be 5 volts, right? Without any signal. Still you will have 5 volts of a common mode voltage. So we will use VG as 5 volts.
Ma'am, shouldn't the equation be 12 minus Vx?
Yeah, it is 12 minus Vx, no?
Last second step you have written 12 minus K, ma'am.
Oh, acha, acha. It is Vx, Vx, Vx. Yeah, so it is Vx minus 5 minus 1 whole square. And here you have 12 minus Vx. So 2 times Vx minus 6 whole square, here 12 minus Vx. So the final equation will be 12, 2Vx plus 16 minus 3Vx is 0. So we have to solve this equation to find the values of Vx. So here we would get two values for Vx. The first is 7.5 volts and another one is 4 volts. So now here we have already observed that Vg is 5 volts.
मैम
Yes,
ये नीचे से तीसरा लाइन में आपका -12 होगा ना, -12 Vx होगा ना।
-12 Vx क्यों होगा?
6 दूनी 12 हो जाएगा ना मैम।
6 कहाँ पे है? वहाँ
टू
Vx
इन
- 6 होल स्क्वायर भी है ना?
यस मैम, Vx स्क्वायर प्लस 36 -2 ए भी होगा ना मैम।
Oh हाँ, so यहाँ 12 हो रहा है ना?
यस मैम,
So this
यस
is
मैम,
24. Okay. So
यस
यहाँ
मैम,
23 हो रहा है, yeah.
यस मैम।
So we have to solve this. We'll get two values, 7.5 and 4. And we already know that VINC, that is the common mode input, at already 5 volts. So we need to have VSG greater than 0, right? In our case. So यहाँ पे अगर if Vx is 4 volts, is it possible to have Vx to be 4 volt to operate your transistor in saturation? Or at least to turn on your transistor? That is not possible, right? So the value of Vs is 7.5 volts. So that means at this point, Vx is 7.5 volts. Now this we know. Okay. So
Mom, can you explain why 4 volts is not considered once again?
yeah, see, your Vg is 5 volts, correct? If Vx is your Vs, right? Which is 4 volts, correct? So in case of PMOS, VSG should be greater than mod of VTHP, correct?
Yes, ma'am.
So this should be Vs minus Vg, which should be greater than mod of -1. Now Vs is 4 volts, Vg is 5 volts. Will it be greater than 1?
No, ma'am.
No, right? So that's why it's impossible to have your Vx as 4 volts.
Understood,
So
ma'am.
yeah, so that's why we move ahead with the Vx of 7.5 volts. So this is what we got. So from here, now if we try to calculate the current ID1 or I1, it will be kW by 2L VSG minus VTH whole square. So this is 200. 7.5 minus 5 minus 1 square. So I1 turns out to be 2.25 milliamperes. Now we have to find this value, right? We have to find the output potential because across this potential only you will have a swing. So to find this V out, V naught 2, if we observe V naught 2, we can see that whatever is the drop across RD1, that will appear as V naught 2, correct? So V naught 2 is I1 into RD1. So V naught 2 is I1 into RD1.
Ma'am, your screen is stuck.
My screen is stuck, but I can see it working, right? So maybe so it's okay for me. Can you check once again?
Yes, ma'am. Now it's right.
Yeah, because my screen is working. Okay. So the V overdrive voltage, or sorry, the V output voltage that we obtain with the DC supply and DC voltage, that is DC common voltages, 3.6 volts, correct? So now, if you have 3.6 volts, so what is the lowest that you can go? Now, let's say this is your VDD, this is ground rail, and here somewhere is 3.6, right? 3.6 volts. Yeah. So here somewhere you will have 3.6 volt. So your output is at 3.6. Now, if I have to fit in a sine wave, what is the maximum swing that I can obtain? See, the swing is always symmetric across your DC point, right? So the maximum swing is limited by this ground node. So this is the swing that you will obtain. So the output swing would be 3.6 volts in negative. 3.6 volts, maybe I should say amplitude. This is the maximum amplitude. Yeah. So this is the maximum that you can get in this particular circuit. So now, so always your swing is limited by one or the other. So it would be either limited by VDD or limited by the ground. So the maximum swing you will obtain by what is the smallest one that will give you the swing. Clear? So with this now we are asked to find the CMRR for the same circuit. So when there is the same circuit again, we know the CMRR, right? What is the CMRR? What is CMRR?
Differential gain by common mode gain.
Yes, differential gain by common mode gain. We know AD. How do we write AD? Since again it's a CS configuration, so the AD would be minus GM into RD. Now in this case, we will figure out what will come as RD. And if we talk about ACM, so the formula for ACM is given by GM into RD upon 1 plus GM into 2 times of RT. So this is the formula that we would get. So now AD will find, so first of all, let's find for what is required, which is Km. This is Kw by L, VSG minus 8HP. Vs was 7.5 minus 5 minus 1. This is 3 millisiemens. Gm is 3 millisiemens. RD we know 1.6 K. So AD is Gm into RD, that is 3 Siemens into 1.6 K. So AD turns out to be 4.8 volt by volt. Now we know GM, we know RD, so we can find ACM as well. So this is 6 millisiemens into RD is 1.6 by 1 plus 3 into twice of RT. RT is 1K. This becomes 4.8 by 1 plus 6. So 4.8 by 7. Now if I find my CMRR, I get it as 4.8 by 4.8 by 7, that is 7. Now if CMRR is 7, then what is the CMRR in dBs? Yes, what is the CMRR in dBs? Can you please calculate?
16.9, ma'am.
Yes. So it is 16.9 dBs.
Ma'am, shouldn't the AD be minus?
We take mod of it because a sign is not important to us in terms of CMRR. It's more about the value, like what is the value. Okay. And also from the values, you can clearly observe that this particular amplifier is not a good amplifier for us as the CMRR is quite low. We want around 120 to 180 dBs in practical scenario. So we can clearly see that this particular amplifier is not uh, possibly a good amplifier for us to use, right? So yeah, moving on to the next problem. So here in this problem, okay, so these problems will be dealing with the capacitances. So before that, let's talk a little bit about the capacitances so that those insights can be used in this particular problem. Okay, so when we talk about capacitances, especially in MOSFETs, since we are dealing with MOSFETs, so we categorize them into separate parts. Okay, so one part is the terminal capacitance. Terminal capacitance means these are the capacitances which you can measure by probing them. Okay, so these can be measured externally by probing them. That's why these are called as terminal capacitances. And these are the capacitances that we are like we have used till now. That is CGS, CDB, CGD, CDS. So these all are terminal capacitances, right? The next branch of capacitances are gate capacitances. This is the capacitance that comes because of gate oxide. So this is basically the COX in your device, right? So these are like so and Then another one is junction capacitance. And these are like, mm, so we have PN junctions, right, in our MOSFET. So we would have two capacitances, one between like a drain body capacitance, and a small capacitance will also come from source body capacitance. So what actually happens is these terminal capacitances that we extract by probing are a result of these two physically present capacitances. So we cannot directly um, measure these like gate capacitance or junction capacitance, but we see their effects in terms of terminal capacitance. They are not separate things, it's just that we bifurcate them uh, depending on how to deal with the problems. That is the idea, right? So now maybe I can quickly draw. So this is our MOSFET. Maybe I should draw a 3D view. So a 3D view would be better and it will give us more insights into it. So now here we have our oxide, and over that we will have metal. So this is the whole thing is our oxide material. And then we would have source, drain. Here you take the contacts. So here there will be the contacts. For gate you would take the contact from here. This is gate contact. Source, drain. Body you can take somewhere here, or you take it from far apart. So that's another concern. So yeah, in our device, this is the length, this is channel length, or we can say gate length. This is the width, this is the height. When we talk about capacitances, what are capacitance? What is a capacitance? dq upon dv, right? So wherever you observe a change in charge because of change in applied voltage, that gives us the capacitance. So we see that this particular oxide which is present over here, over which you have your metal. So this particular region being metal oxide, which is inductive metal. So it is like this particular region is like this is metal, this is metal, and in between you have this insulator or dielectric material. So this is a parallel plate capacitor, right? So your oxide capacitance is actually the parallel plate capacitance that comes because of this effect of metal oxide metal. So from there we directly write our gate capacitance. Yeah. From here we write our gate capacitance as Cox epsilon A by D. We all know it as epsilon A by D, right? But the thing is, we generally talk about per unit area capacitance. So that's why we generally ignore the area. We just write Cox as epsilon upon D, where Cox is in farads per centimeter square or meter square or micrometer square, depending on the units, right? So it is a per unit area capacitance. And then actually what happens is there are times when your gate oxide, so we make source starting at the edge of the gate, right? And this drain also starting at the edge of the drain. But this is not possible physically. So some of your source and drain actually diffuses into under the gate region. Okay. So in this time, this particular region, your source and gate diffuse a little bit while fabrication, and you get this extra regions over here. These will give you overdrive capacitance. We call it COV or overdrive capacitance, or we'll say overlap capacitance. So overlap between your gate and source region and gate and drain region. So this can be COVD and COVS, but we deal it in the same way, that is epsilon by D. And also mind you that now your effective gate length is actually this. So this is L effective. This is the actual gate length of your particular device, right? Because channel is formed at the surface. It's very thin. So that particular cross section only should be considered. So yeah, these are a category of capacitances. We call them gate capacitances. Now, the second category, as we discussed, they are junction capacitances. So these junctions are PN junctions. So these come from the PN junction. So here we have NPN, let's say. So the junctions are formed between um, source and body or substrate and drain as well as the substrate. So these are also again the junction capacitances We call them CJN. And these junction capacitances are given by the PN junction based capacitance formula. So that formula is epsilon Q NA upon 2 Na plus Nd into VBI. Okay, so if I write it in letter V, to be twice of Na plus Nd into VBI. And when we talk about VBI, how do we find VBI? So we find VBI by KTLN NAND upon Ni square. So this is how we find the VBI of a given junction. So these are the formulas that we will be using. So this is not, so this is without bias. So this is the ideal condition when there is no biasing or zero voltage is applied across all the terminals. Now the junction capacitance with bias is given by CJN, and that is CJN naught by root under 1 plus V bias by VBI. Okay, so this is the formula. So at the end, the formula that we need to use is this one. Because we will be using them with the bias, right? So it depends. If it is without any bias, so we'll go with VBI only, and the built-in potential of the junction. But when bias is involved, the capacitance changes with the bias. That's why we will be going with the bias condition. Whereas when it was gate capacitance, here we can clearly observe that the gate capacitance will never change, considering that both sides have already become metallic with high electron concentration on one side and metal on the other. This gate capacitance will never change. So yeah, with this information, let's move ahead and solve the problems. So in this problem, a CMOS inverter is designed as shown below. So this particular circuit is an inverter. So when you apply like one voltage here, like let's say positive input here, you will obtain a negative input on the other side. If you apply 1 here, you'll get a 0. If you apply -5, you would get 5. You would apply 5, you'll get -5 volts. So basically, it's a digital inverter that we all know. So the length of both the NMOS and PMOS is so length of both the transistors is 0.18 micrometer. Width of NMOS is 1.8. Width of PMOS is 3.6. NA is given. ND is This is NaND for NMOS. Now for PMOS, further the depth of the doping for drain and source is 1 micrometer. So depth of drain and depth of source. So let's denote them by ds and dd, which is 1 micron, that is 1 micrometer. And the length of the drain region. So this is basically this is L is the length, and this is ds, this is also dt. Okay, so this is depth and this is length. Ls and LP are given to be 0.18 micrometers. So now these are given. It is given that if the voltage at the output is 0.9 volts, what is the total junction capacitance between the output node and the ground? Give your answers in femtofarads, and Vt is 36 millivolts. Okay. So it is already mentioned that we have to find the junction capacitance. So we need to find the junction capacitance. Let's find the junction capacitance at the zero bias first. So junction cap at 0 volts. So that is the one that comes because of doping. So J and CJ and naught. The formula was 7Q ND by twice of Na plus Nd into VBA, right? So for this, we need to find the VBA, which is KT ln NAND upon NI square, or it can also be found out as no, ठीक है. NAND upon NI square, say, let's find out. So NI we know, NI is 10 to the power 10 in case of silicon. So considering silicon, right? So for silicon, epsilon silicon is also 11.8 into 8.85 into 10 to the power minus 14 in CGS units. That is centimeter gram seconds. Okay. So we are not talking about meters anymore. We'll be describing things in centimeters now. As you must have observed that the concentrations which were given were also in per centimeter cube, right? So the areas and everything, we try to uh, like state them in per centimeter square or in centimeters. So CGS units will be used to get the answers. Okay. So VBI is 0.026, that is 26 millivolts, ln NA upon Ni square. So we need to find it for both N transistor as well as P transistor. So VBIN, it's NMOS, so it is 0.8 into 10 to the power 17 into 6.2 into 10 to the power 17 into 11.8 into 8.85 10 to the power minus 14 by twice of 0.8 into 10 to the power 7 plus 6.2 into 10 to the power 7 into, oh, one second. Oh, sorry. I've started using this junction capacitance formula. NA. So it is NA upon Ni square, right? We are finding VBI. Yes. So this is NA upon 10 to the power 20 Ni square. So similar way, we will be finding VBIP, that is 0.026 ln 1.7 10 to the power 17 into 10.9 into 10 to the power 17 by 10 to the power 20. So yeah, what is the value of VBIN that we find out, and what is the value of VBIP that we find from these formulas? So make sure this is ln. So this is ln is log base e. So please don't use log base 10, otherwise the answer would be wrong. So what is the value of VBIN and VBIP? So let's call it Vn naught and Vp naught. That is Vp and Vn at the 0, bias.
Zero point nine one.
0.91 for which one? Is it for N or for P?
P, ma'am.
Okay. So this is 0.914 volts. What about N? Okay, so you people can find out it is 0.879 volts. Okay, for NMOS. This is at zero bias. This is also at zero bias. So now from here we can find CJN naught and CJP naught, the junction capacitance for N and P at zero bias, which is epsilon silicon Na ND by twice of Na plus Nd Vn naught. Here it would be epsilon silicon Na Nd by twice of Na plus Nd into Vp naught. So maybe you can try finding one. So other one would be in the same way. You just need to be a little patient because there are a lot of terms that will come into picture. So this is 11.8 into 8.85 into 10 to the power minus 14 into 0.8 10 to the power 17, 6.2, 10 to the power 17 by twice of 0.8 into 17 plus 6.2 into 17 into 0.879 volts. Yes. So anybody, can you find the value for this? This is the junction capacitance with zero bias. Please calculate for this one. I'll let you know the values. This will come in farad per centimeter square. This will also come in this.
7.70 into 10 to the power minus 7.
7.70
Yes, ma'am.
into 10 to
Into
the
10,
power.
7, minus 7. Sorry.
Oh, so the answer that I have is 8.2 into 10 to the power minus 8 for this one. Maybe you can check it once again. थोड़ा
Okay,
बहुत
ma'am.
ऊपर नीचे हुआ होगा.
Okay, ma'am.
But yeah, and for other one, it is 11.817 into 10 to the power minus 8. Okay, so first of all, the thing that we need to keep in mind is junction capacitance, or even if we talk about capacitance, capacitance always needs charge separation. So there needs to be some separation to get a capacitance, okay? So we know that in forward bias, the junction is almost negligible, right? So always when we talk about junction capacitance, we are more concerned about our this reverse junction that we have. This particular reverse junction that we have over here, that is what is our main concern. Okay, so this junction is what we are concerned about. this particular one. So that's why the potentials and everything that we talk about are VDS. So here when I say junction with zero bias, that means my VDS is zero. Junction with some bias, so that means there is some bias at my VDS, because reverse bias gives you that separation in charge and which will lead to capacitance. Okay, so that's why. So this is at VDS equal to 0. This is at VDS equal to 0. Cj n naught, Cj p naught. Now we have found out Cj n naught, Cj p naught. The next step is to find Cjn. Cjn and Cjp. So these are Cjn naught by root under 1 plus V bias by, yeah, V bias by VBI. So basically VDS by VBI. And here it is also Cp naught, Cjp naught root under 1 plus VDS by VBI. So we already know the value of Cjn naught, right? 8.2 into 10 to the power minus 8 by root under. What was the value of VDS? Is in this particular circuit, what is the value of VDS? This value is the VDS, right? That is already given. So VDS is 0.9. So 0.9 by VBIN was 0.879. 0.879. And similarly, the other one, it is 11.817 by root under 1 plus 0.9 by 0.914. Yeah, it is 0.9. So the final values of the capacitances are, the final value for P is, so can somebody find these values, like final values? What is the value that you get over here? So I don't have that
5.763 into 10 to the power minus 8.
for which one?
First one.
First
First
one,
one.
5.763
763.
into 10 to the power minus 8 farad per centimeter square. So I don't have these answers. You people can check. But yeah, and second one, do two times, almost two, almost close to 10, 1.8 to 10.
8.388. 388.
8.388. Acha, okay.
Yes, ma'am.
Into 10 to the power how much? Minus 8 only. Okay, so you people can check this. But now we are not done yet. So this is C, this is capacitance per centimeter square. This is also capacitance per centimeter square. Here in question, what is asked? you have to give your answers in farads, that is femtofarads. So, which gives a clear idea that we have to find the actual capacitance rather than capacitance per unit area. And also, since the dimensions are given to you, so that already indicates that since the dimensions are given, you have to find the capacitance, the total capacitance, including the area, right? So, as I mentioned, we will only have the this depletion capacitance or junction capacitance at the drain side. So that's why we will only look at the Q that will be there at the drain side. The cuboid that will be formed at the drain side, we are only concerned about that. Okay, so yeah, yes. So this is the junction that we will have. This is the drain side. So here we have the length of the junction. This is like length of the doping, drain side doping, depth of the drain side doping, and this particular width is actually the width of the transistor. The total width is doped. Okay, so this is the complete width. Now, when we talk about where all the junction will be formed, right? So if we see this particular diagram in 3D, yeah, so this is the diagram in 3D, right? So now if I transfer this, okay. So if I transfer this here, gate source drain. So looking from here, we can see where all the junction is formed, right? So this be the black only. So one junction that will be formed, the junction will be here. So this is the depth of the doping side and the whole width, right? Do you understand? So this is the inner width. So the inner face, that inner face we have, no? This face. So this is, let's say, if we name the faces, so this is face one, face two, the front face, the the side faces, let's say face three, the back face is face four, top is five, and the bottom is six. So the cuboid has six faces. So we will be dealing with all six faces and we'll see where all the junction will be formed. Based on that, we will calculate the junctions. Okay. So first off, we know that the innermost face, face one, will have a junction, right? This is with the substrate. So face one will have the junction. So face one, junctions at one. Then if face one has junction, now see the bottom face, this bottom face, this one. the bottom face of the cube, that is face 6, it will also have a junction, right? Because it is in contact with our body, correct? With the substrate. Similarly, the face opposite to face 1, that is the face 3, it will also have a junction. It will also have a junction because this particular transistor will be connected to some other transistor. While fabrication, you don't fabricate one transistor on a one die, right? You fabricate multiple transistors on a single die. So when there is a P well formed for a PMOS, sorry, for an NMOS, then many transistors side by side are fabricated. So that brings us to the point that, okay, phase 3 will also have a junction, right? So phase 3, the side one opposite to 1 will be having a junction. Now, this particular transistor, so it is doped in between. Okay. So the doping is all in between. So that brings us to the only phase which will not have any doping is the top phase. Because from there you will extract the contact. Other than that, all 5 faces, all the round faces, the surrounding faces, and the bottom will have junction. So, which brings us to the faces that will have junction are 1, 6, 3, 2, and 4. So, 1, 2, 3, 4, and 6 basically. So, the faces that we need to consider are 1, 2, 3, 4, and 6. That is the bottom face, right? Now, if I talk about the areas, so areas, how should be right? It is the area of first phase, that is DD, the depth into the width. So, and twice of that. So, depth into the width plus 2 faces of front and back, that is twice of DD into LD, and one of the bottom face. So, bottom face will have LD into W. Is this clear how we found out the area? Any doubts in the area? I hope there are no doubts in the area, especially the junction faces or anything. If anybody is feeling like why this face is considered, why this is not considered, you can please feel free to ask, okay? So yeah, with this we know that these are the faces that will come, and this will come for both NMOS and PMOS. The only thing is we have to substitute the values and find the areas. So we know in both the transistors here, the only thing that changes is the WN and WP. Other than that, all of them are same, like DDDS. So depth, doping depth and length of doping are same for both the transistors. The only thing that changes is this, which is the width side. Yeah. So now for if I have to find for NMOS the area, it would be twice of 1 into 1.8 twice of 1 into 0.18 plus LD, that is 1 into W. So this is 1.8 micrometers. Similarly, for PMOS, the area would be twice into 1 into 3.6 plus 2 into 1 into 0.18 plus 1 into 3.6 micrometers. So all of you, please calculate these areas, but make sure you find the areas in per centimeter square. Okay? I'd be back in a minute. Please find these areas. Okay, so did you people find the area? It should be in centimeter squares. So what is the areas that you get for NMOS and PMOS? Hello, am I audible?
Yeah, for PMOS 11.16.
For PMOS, it is 11.16.
Yes. Oh, sorry, in micrometer.
Yeah, it's in micrometers, right? So, anyways, so maybe I would write it down. So you have to find it in centimeters square so that the capacitance that we are finding in per centimeter square. So the units can be nullified. That's the only reason. So for NMOS, the area that I've got is 4.284 into 10 to the power minus 8 centimeters square, whereas for PMOS it is 8.208 to the power minus 8 centimeters squares. So the total capacitance at the end is CJN into area and mass plus CJP into area PMOS. So at the end, the total area, the total capacitance turns out to be 9.199 femtofarads. Femto we all know, right? 10 to the power minus 50. So 9.199 is the answer. Is this clear? How we deal with the junction capacitance, with junctions to consider everything?
Yes, ma'am.
So whenever this type of problem is there, if it is hard to visualize, please try to draw them. First draw them in a 3D and then visualize, okay, what are the things happening, which phases to consider, which not to consider. Okay? Yeah. Now with this, so let's say if I ask what all phases you would consider to calculate the total overlap capacitance. Okay, so let's say, let me make it a straight line so it would be a little easier for us to visualize. I say this is my extra overlap region, the red one. Okay, this red one is the overlap region. What I want is the value of overlap capacitance. So this is again a cube or cuboid. So it's a cuboid and it will also have 6 faces. So which all faces of this cuboid now will have the junction for overlap capacitance of junction? Yes, which all faces would we consider for overlap capacitance? If we had to find it from like junction capacitance formula. So where all the junction will be formed in this case? How many faces out of 6? Earlier we had 5 faces with junction. How many this time? I say 5. How many of you agree with me?
Four, ma'am.
Okay, 4. So one option is 5. Option A is 5 faces. Option B is 4 faces. Any other answers? Yes, any other answers? Okay, so how many of you say 5? And how many of you say 4? Okay, I got one saying 5. What about others? One says 5, one says 4. I say 5. What about others? Okay, another 5. Anyone who is supporting 4? Okay, so the actual answer is 4 faces. 5 faces is not correct. Now let me explain you why. See, you have 2 faces coming from front and back, correct? One of the bottom face will have a junction. One of the side faces will have junction which is parallel to 1. But the face which is connected to the drain doping already, that junction, there is no junction over there. It is junctionless. When is a junction formed? When you have doping differences, right? But since it is the part of drain itself, so the face which is connected to the drain side, there is no junction over there. So when there is no junction, there won't be a junction capacitance over there. So actually the number of faces now you have to consider are only 4. Am I clear to everyone?
Yes, ma'am.
Yeah. So that's why whenever you get a question or any problem, try to think with the basics, very basics. See, junction for junction, what you need to know is there should be doping difference. But you know, this overlap is part of drain itself, right? So because of that, you don't consider it that particular phase which is coming in drain junction, like finding the drain junction region. So that's the thing. Okay. So yeah, the correct answer is 4. I don't know the name who said 4. So somebody said 4. What was your name? If you can respond. Who was that? The only person.
Yes, ma'am.
Okay, so what's your name?
Niranjan, ma'am.
Sorry,
Niranjan.
Niranjan. Nice
Yes,
Niranjan. So
thank you,
you
ma'am.
paid attention. So that's good. So yeah, so try to be a little attentive in class. But yeah, that's something very important. So just in case, in future, if somebody designs it like this, so you need to be a little visually active in this type of situation, right? Because first of all, we always deal with MOSFETs as a 2D figure, but we should visualize it 3D, especially when you are calculating um, all these capacitances and stuff. So be a little visually like you should be able to visualize things to deal with these problems. Okay, but I understand this problem is very big. So there are chances that in exams like um, GATE and all, this lengthy problem won't be there. But there might be a possibility where junction capacitance per unit area are given, and you have to find the areas and find the total capacitance. Those type of small chunks can be adjusted. So half of this problem can be one problem, another half can be another. So this problem can be divided into two for you to deal with in GATE or any such competitive type of exams. Okay. So yeah, with this, let's move on to the next problem. So here again, we have the problem based on same particular circuit. So, Okay, so in the previous question, when I said I am with five voices, actually I was bluffing. So sometimes I might also bluff you people, especially when I ask you a question and I support with a question. Most of the time, the chances are I might be bluffing. So yeah, that's when you be a little attentive and think what I'm asking and think from very basics. Okay. So yeah, now in this particular problem, we have voltage input at 0 volts. And what is the total capacitance between the output node and ground? So again, the same capacitance has been asked, and this should be in femtofarads again. So now, uh, as we know, this is an inverter. Whatever you give in input, the opposite will come out in the output. So if you give 0 volts in input, you would get VDD at output, and vice versa is also true. Okay. So here, if you give 0 at input, your output is at 1.8. So what here we need to do is we have found out Jn naught, right? So Jn naught will remain same. So Jn naught will not change. So the only thing that changes is the bias voltage. So from the previous problem, everything remains same, only we will change the bias point and we'll get the answer. Areas will also remain same. Okay. So this will remain same. This will change. So here instead of 0.8, we'll write 1.8 and we have to calculate this value. Similarly for P, yeah, again here, this would be changed to 1.8. So based on this, we'll get junction capacitance per unit area for both of them. We know area and area P, which was 4.284, 8.208. Centimeter square, centimeter square. These junction capacitances for N and P are 4.697 10 to the power minus 8, 11.817 10 to the power minus 8. By using these values, the C total comes out to be 11.505 femtofarads. This is the total capacitance that we obtain by changing the value. So earlier the capacitance that was obtained was 9.19, and this time the capacitance has increased to 11.505. So higher the reverse bias, the more capacitance has been obtained. Now, moving on to the next problem, again in the same circuit. Okay, in the same given circuit, it is asked to assume that Cox is 7.5 femtofarads per micrometer square for both N and P. Cox N, this is also equal to Cox P. Now the length and width as declared earlier. Assume the overlap capacitance between gate drain and also gate source are 0.95 femtofarads per micrometers, and the input is now 1.8. The input is now 1.8. What is the small signal incremental capacitance seen looking into the input given femtofarads? See, if your input is at 1.8 volts, the output will be 0. So when the output nodes both are, so VDS is 0, right? So VDS is 0 means there won't be any capacitance present other than the zero bias junction capacitance. But here in this problem, what is asked is the gate source capacitance that will appear in the input side. So at this point, what is the capacitance that you would find? This is something that you need to find out. So in this case, if we see from small signal analysis, the capacitance that will appear at this point is first of all the CGS, the CGS, then the CGD and the CGD. Correct? So from small signals, we are very clear that these are the capacitance that will appear. Now, first of all, since this is so in these transistors, if you observe something very carefully, always in a transistor, your CGS should be greater than VTH, correct? Or CSSGP should be greater than VTH to turn it on. But in this transistor, if you observe, this is source, gate, drain, source, gate. For the PMOS, the gate and source potential are equal. So VGS is 0. So if VGS is 0, that means this particular transistor, that is PMOS, is off, whereas your NMOS is on. Correct? So when your PMOS is off, see the capacitances. Now we are dealing with our CGS and CGD. So in CGD, so let's say capacitance will be Cox and Co drive. So if transistor is off, if the transistor is off, the only capacitance So we will have CGS and CGD. So in case of CGS, the capacitance that we will obtain is the overlap capacitance because it is off. So in case of transistor off, there won't be any channel formed. So COX won't be there, because of which your CGS will be C overdrive. Now, if we talk about gate and drain capacitance, so again, we know that on the drain side, the potential is at zero. So that's why it will be again C overdrive. Now, let's say if the transistor is on. So if the transistor is on, that means the channel is formed. Okay. So if the channel is formed, that means the oxide capacitance will also come into picture. So considering that we distribute the oxide capacitance equally between gate and source. Okay. So we are distributing the oxide capacitance half half. Half is the share of gate, like drain, and another half is the share of source. So depending on that, now if I want to find my gate to source capacitance, so overdrive capacitance will be there. It will be there anytime, anyways. The other capacitance that will come into picture because of this is half of Cox. Okay. Similarly, when we talk about CGD in the transistor which is turned on, you will have C overdrive and the another half of oxide capacitance that is coming from the drain side. So half of Cox. Okay. So this also depends on what is the region of operation of the transistor, like whether it is linear or saturation or cutoff. So this is for cutoff. This is when the transistor is in linear. Now, when it is in saturation, we know that on the drain side, the channel reduces and we have most of the channel on the source side, right? So, according to that, your formula of this oxide capacitance changes. It depends on the region of operation. So, here in this case, if you observe very carefully, your transistors, like an in an this inverter, your transistors will only operate majorly in two situations. Either it is cutoff or it is linear. If it is giving you like 0 and 1. So if the outputs are completely opposite of one another. Okay. So now based on this, the capacitance in Cin will be, we know that the this inverter has a gain of 1, right? Inverter is gain of 1. So that's why the gain into CGD will again come out to be CGD. So the capacitances that will appear are CGSN plus CGDN, CGSP plus CGDP. Okay, so here we have to substitute. Now this is in linear, this is in off. So accordingly we have to use the values. So this is COV plus half COX plus CO drive plus half COX plus CO drive plus CO drive. Right? So it is 1, 2, 3, 4. 4 times C overdrive plus COX is the total capacitance that we get. Now COVs were same, so that's why I wrote them down together. And COX, so it is 4 times of 0.95 femtofarad plus 7.5 femtofarad. So the capacitance at the input terminal is 11.3 femtofarad per micrometer square. Okay, is this clear?
Yes, ma'am.
Yeah. So with this, let's move on to the next problem. So in this particular problem, an input is applied to a CMOS inverter such that the output is at 0.9. So this happens if the input is at 0.9. So yes, when your input is half VDD, the output comes out to be half VDD for an inverter. Okay, so here it is given 0.9 volts. At this operating point, GMP is 3.2 millisiemens. GMM is 3.2 millisiemens. R naught P is 17.5 kilo. R naught N is 17.5 kilo. At this operating point, estimate the capacitance seen looking into the input of the circuit. So here you have to find the capacitance. Cn. Give your answers in femtofarads. Assume that the devices are well beyond pinch off. Okay, they are well beyond pinch off, and CGD of both the transistors are purely overlap capacitance. So CGD is C overdrive. So it is given that CGD is C overdrive, and you have to find the capacitance, input capacitance. So earlier also we found this. So this will be a combination of CGS and CGD, right? So we know from small signal ADS minus GM GMP upon R naught N plus R naught P. This is your AD, and we know that CGD dash is 1 minus AD into CGD from the Miller effect. Now, CGD dash is 1 plus CGD. Okay, so Cn will be CGS n plus CGD dash n, CGS p plus CGD dash p. Now here, in this particular case, when your input and output both are equal, if you will see your VGS minus VT dash is less than VDS. And similarly in case of the PMOS as well. So basically, your transistors are in saturation. Okay. So when your transistor is in saturation, most of the channel remains towards source side. Drain side, you don't see any channels. So earlier, as we have used half Cox in case of CGS, uh, here we can use full of Cox in case of CGS. That is because all of the channel is towards the source side. Here, if you observe in the problem, it is given that assume that the devices are well beyond pinch off. That means the channel has shifted almost towards source. Okay, so that's why we will use directly the total COX over here. So for CGS in, we would get CO drive in plus COX in plus CGDN would be 1 plus Gn GMP by R naught n plus R naught P into C overdrive. Plus similarly for the PMOS, it will be C over P, C ox of P plus 1 plus GM, GMP, R naught N, R naught P into C overdrive. Since it was given in the problem that CGD is only due to overdrive capacitance. So with this, if you observe the values of C overdrive and COX and C overdrive, so here 7.5 and 0.95. So the difference is very high. C overdrive is much less than COX, right? So CGS, we have considered COV plus COX. It is also equal to, like, it is approximately equal to COX because CO drive is very small. So you can use this value or you can also neglect this value. It will not make much difference. So from there, if I write it in a smaller version, if you simplify the formula, it will be COX in plus COX P plus C overdrive n plus uh, C overdrive P into 1 plus GNM plus GNP by R naught n plus R naught P. So this is not whole, this is just here. Okay. This one is outside the division. So the final Cn value that we obtain is 304.83 femtofarads. Right? So moving on to the next problem. Here in this given circuit, C is 2.2 picofarad, CD is 1.3 picofarad, RD is 13.1 kilo ohm, small RDS is 21 kilo ohm, Gm is 1.6 millisiemens. So the overall transfer function of the circuit Vr by Vn is to be computed. Use Norton's method. What is the pole and the output impedance of the circuit? Okay. So here the input is coming from this point and this is the output. From here you have to observe the um, pole, right? So we know how do we write pole? It is 1 upon R into C. So what all are the resistances that you will be looking from this point? So one is, this is B. So here should be small rds at point A. At A, the resistances R effective would be RD parallel to small rds, correct? And what is the capacitance that you see C effective? It is CD because the terminal capacitances, C's are not given. So considering that all of the capacitances have already been included into CD. So from there, if we find the value of pole, so pole would be at 1 upon RD parallel RDS into CD. That is 1 upon 13.1 into 21 by 13.1 plus 21 into 1.3 picofarad. So when we compute this, what we'll get is 21 plus 13.1 by 13.1 into 12 into 10 to the power 6. Here it is 10 to the power 3 into 1.3 into 10 to the power minus 12. So after solving this, the pole value turns out to be 95.35 megaradians per second. Is this clear? So rather than computing, we already know that how to find the poles and zeros at a point, right? At the given position. So you have to calculate the value of effective resistance at that particular point and also the effective capacitance looking from that point, and then we simply calculate 1 upon RC. So this is in radians. If you want it in hertz, that is the pole frequency in hertz, it will be 1 upon 2 pi into RC. Okay? Is this clear? All right. So we are done with the problems which were decided for today. So that's all for today. If you have any doubts, feel free to ask. Otherwise, we'll meet next week with a new set of problems. Any
Thank you,
doubts?
ma'am.
Okay. Thank you.
Thank you, ma'am.
Thank you. Thank you.